This lecture is on nature and sound waves. There's some calculations here that we'll see as well. But there's a lot of definitions that you should be aware of. So first, we know that light reflects. Light is a wave, and that kind of gives us the idea that sound would reflect as well. And there is a possibility for sound to reflect, and it follows all the same laws of reflection that other waves do. So sound obeys the laws of reflection. For this reason, we can create structures that make use of this reflection. This here is a picture of a dome that is designed in such a way with kind of parabolic sides. It's actually, it says here, this is from St. Paul's Cathedral. It says whispers can be heard clearly 32 meters away. But there are dome kind of curved reflectors that can be used. I remember they used to have something set up at Toronto's Pearson International Airport where you could hear this. It was an art structure that might still be in place. It's been a bit since I've been there, but echoes are something else that you can that occurs when we have reflection. So sound will produce an echo if the sound reflects off of a hard surface and returns to the speaker or the person who or the thing that produced the sound. So we can use this concept of sound echoing or reflecting in a number of different applications. The most important might be sonar, which is short for sound navigation and ranging. For example, this fishing boat, it can send out a sonar signal to try to detect if there's a school of fish. And if they hit the seabed, and they see the measurement of the distance as being very far, they know that there is no fish in that range. But if they end up hitting something like a school of fish, they would know that something that would be shorter than the length of the seabed, they would know that there is possibly a good catch on their way. Radar uses not sound waves, but radio waves. And it's radio detection and ranging. And radar is used in aircraft today. It's used to predict whether it's going to rain and other meteorological events. It's used to predict the movement of storms and hurricanes as well. Another use of reflection is to find oil deposits or natural gas deposits. This is done by using a vibrator truck to send waves through the ground, and then sort of measuring to see if those waves return, if they echo off or reflect off of a source of gas or oil underneath the ground. If you have a cat or you've seen a cat, you might have noticed that cats' ears are designed in the shape of kind of a half cone. It's actually that's actually done by design. Cats' ears are called pinnae, and they can amplify sound by reflecting any sound that goes into their ears down towards their cochlea so that they can understand the sound and hear very well. Cats actually have some of the best hearing among any mammals. It says, note, cats can see in dim lighting, but in doing so, they sacrifice some detail in the perception of some colors. As a result, cat vision is poor up close. They often compensate for this by using their large pinnae to detect the high-pitched noises produced by their prey at the end of a hunt. They actually can hear very high pitches as well, which helps them hunt smaller animals that make squeaky kind of noises like mice and rats. Dolphins use echolocation to reflect sound off of solid objects as well. This helps them find fish. Bats use echolocation to find insects that they'd like to eat and to find the walls around caves so that they don't hit into them. Other animals also use echolocation. A dolphin, actually, this goes in a little bit more about how dolphins hear. They actually have an organ called a melon that produces these sound waves, and it also helps them when that melon vibrates. It helps them understand just how much or how far away something is, and if something was a solid object or not, or a fish or something else. And then again, we have bats. So echolocation, sonar, other kind of things we can write down here. This is all applications of the reflection of sound. Now here's some questions you might get based on reflection, and there is something interesting we have to consider, is that the distances either have to be doubled or halved based on what the question says. So this question here says we have a woman makes a sound, and 3.5 seconds later her echo returns to her. How far is the wall, assuming the speed of sound is 350 meters per second? So in this case, our velocity is our distance over our time, and we're trying to find out our distance. So the distance traveled is velocity times time. Our distance traveled is 350 times 3.5. So what is 350 times 3.5? We have 1,225. That's the distance traveled, but we have to know that the distance to the wall would be half of that. So we'll also have to do this calculation. And if I divide this by 2, I end up with 612.5. So therefore, the wall is 610 meters from the woman. Let's try another question. A ship is traveling in a fog parallel to a dangerous cliff-lined shore. A boat whistle is sounded and its echo is heard clearly 11 seconds later. If the air temperature is 10 degrees Celsius, how far is the ship from the cliff? So using V equals D over T and V equals 331 plus 0.6 T, we can start working out this solution. We are trying to find out how far the ship is, so D equals V times T, but we're going to replace that with 331 plus 0.6 T for temperature times T for time. 331 plus 0.6 times 10, and the time it takes is 11 seconds. Now we're going to have to divide this by 2. So let's calculate what it is first. 331 plus 0.6 times 10 times 11. This is our distance. Divide that by 2. And we get 1853.5, or we can say therefore the ship is we'll say we have 2 significant digits here, so we'll say 1.9 kilometers from the cliff. Okay, that's that question. Next one here, it says a ship is anchored where the depth of the water is 120 meters, and they send an ultrasonic signal down to the bottom, and it returns in 0.16 seconds. What is the speed of sound in water? So for this one, we'll look at this one a bit differently. So if the depth is 120 and the signal returns in 0.6, then the time for half of that to occur would be 0.08. So what is the speed of sound in water? V equals D over T. That D is 120 divided by 0.08. I'm just putting it in the calculator. I'm not showing it to you at this time. But it works out to V equals 1,500 meters per second for that question. And I think we're at our last question. Nope, second to last. It says, ultrasonic sound is used to locate a school of fish. The speed of the sound in the ocean is 1.48 kilometers per second. And the reflection of the sound reaches the ship after 0.12 seconds. So how far is this school of fish? Well, let's first cut the time in half. 0.06. And then we will use our D equals VT equation. So D is 1.48 times 0.06. This time I'll turn the calculator on. It's okay. 1.48 times 0.06. And we get, after rounding for significant digits, 0.089 kilometers. This is our solution. These aren't really terribly difficult questions. Here we say, the question says, why do bats need such high frequencies for echolocation? Well, if they're trying to find a small prey, they need to have a high frequency or a low wavelength in order to actually reflect off that prey. It says, estimate the size of the smallest object a bat can detect. This would have to be the wavelength, because if the wavelength is larger than the thing you're trying to detect, it won't be able to detect it. So estimate the size of the smallest object a bat can detect using echolocation if we have an air temperature of 22 degrees. And we have a frequency of 110 kilohertz. So here, we first need to find, let me just move the question up a bit. So we first need to find what is our speed. We can find that using 331 plus 0.6 t. We know our frequency, so V equals F lambda is the other thing we have to relate this to. So our lambda would be V over F, or 331 plus 0.6 t over F. Lambda would be 331 plus 0.6 times 22 over 110 times 1,000. Let's see what we get here. 331 plus 0.6 times 22 divided by that value, we would end up with a lambda of 3.1 millimeters. That's our minimum. So that would be what we can find with this bat.